regulated. And so you'll see that the title is Technology versus Regulation, and that is an unfortunate conjunction, versus, but unfortunately, as you'll see, that seems to be the case. And so I'm really trying to work through some of these ideas about how, first of all, how to develop technology, how to encourage the development of technology, and then how to regulate appropriately and have an appropriate regulatory structure that is both efficient and effective. And you will see later, I think, that in this area, regulation is both inefficient and ineffective, which is a really bad combination. No one likes it. So with that preliminary remark, the outline here, why methane leak detection is difficult. Secondly, emission sources and detection methods, sort of a deep dive into some ways that I think are good ways of going at it. I'm going to talk about current leak detection and repair regulations, and then objectives and methods of rational regulations. That's sort of what's coming. So let's get started with why is methane leak detection difficult. First of all, just as a prologue, I don't have a ton of slides about how important methane is as a greenhouse gas. I'm kind of assuming that most of you are aware that after carbon dioxide, methane is the second most powerful greenhouse gas in terms of its radiative forcing on the atmospheric chemistry, and also with respect to the amount that's emitted. It does have a shorter lifetime, which is a good thing, which also means that because it is a powerful greenhouse gas with a short lifetime, the fastest way to sort of approach a 2-degree objective is to deal with methane, because taking that out of the atmosphere is the fastest way to lower the ultimate temperature. All this is wishful thinking, of course, but anyway, that's the total document. So let's just talk about easy and hard pollution detection problems. This is a easy pollution detection problem. These two women are standing on a big pile of coal. And so if you want to know how much carbon dioxide is going to be emitted by your power plant, you can pretty much just measure the pile of coal. And then there's various heat factors and so on, and CO2 emission factors, and I think you all know that stuff. But basically, carbon dioxide is, in almost all cases, emitted purposefully for an economic or industrial purpose. You know the inputs, you know the outputs, and probably you can get CO2 anthropogenic budgets to, a few percent without even working very hard. You don't really need to make any measurements, except for some lab stuff. You just need to measure the piles of coal, the tanks of natural gas, the barrels of oil, and so on, and there you go. That's what I call an easy pollution detection problem. This is a hard pollution detection problem. This is a photograph of me at the Southwest Research Institute 2 years ago, hunting for methane leaks. Methane, before it's odorized with odorants that make it safe to use in the home, is an odorless, colorless gas. It disappears instantly into the atmosphere. I'll tell you, in a 5-mile-per-hour wind, it is very hard to find small leaks. Using this approach, which is called Method 21, specified by the Environmental Protection Agency. So because it's not emitted purposefully, you have to go find the leaks, and the leaks are accidents that people say, hey, I did a good job welding this, should be no problem, but yeah, no, there are problems. So this is a hard pollution detection problem. Now, what is the magnitude of this problem? Well, U.S. gas industry, oil and gas industry, because oil also produces natural gas as a byproduct. But there's 1 million producing wells, roughly speaking, in this country, 400,000 miles of gathering pipeline, 5,000 gathering compressor stations, 700 gas processing plants, 300,000 interstate gas pipelines. I could go on, but this is an enormous industry. It's highly dispersed industry. Some parts of it are concentrated in industrial sites. That helps. A lot of it is spread out across the landscape. That makes it very difficult to send teams to go find leaks. So, and then multiply this, right, by a large factor for the rest of the world, where generally speaking, environmental conformance is no better than the United States. I mean, we can name a few exceptions. Norway, yeah, absolutely, go to Norway. But rest of world, Russia, which is the second largest producer of gas after the United States, not so much. So, so it's an enormous problem. Now, there has been an enormous amount of intellectual effort and ingenuity directed toward understanding the relationship between top-down measurements, which are basically measurements of the methane concentration in the atmosphere as we observe it, and bottom-up, which is some sort of inventory of possible leaks from various natural and anthropogenic sources. And this work has been marvelous. There are papers in the Proceedings of the National Academy of Sciences, in Science Magazine, Environmental Science and Technology, you name it. People have devoted a great deal of effort to this. And people say, oh, I'm a top-down person, I'm a bottom-up person. Yeah, well, then there's also the routine measurements, which are a different world altogether. So in your academic approach to is it top-down or bottom-up, which way is better, first of all, you're doing research-grade measurements, often by graduate students who are sort of committed to doing a good job, for publication in big government reports or scientific journals, supervised by university faculty, several levels of quality control, including those pesky competitors at other universities. And cost is important. You've got to meet your budget for your funding agency, but the important thing is to get good data. The other half of the world, which is actually 95 or 99% of the world, is routine measurements, where surveys are done to find leaks in myriads of components over all those well sites and all those pipelines and whatever. An important factor is that these leaks do not pose, by and large, do not pose safety concerns. I can tell you, people in my former industry, oil and gas, are really committed to being safe. That is something that is hammered in every day. But the size of leaks that we're talking about are sort of below that level. They're far below explosion limit, but because there are so many of them, the atmosphere is big, but nonetheless, these are powerful greenhouse gas warming agents. And so it's not a safety hazard, so, okay, maybe not quite the same level of commitment to finding them. The personnel are not graduate students, they're not university faculty, they are people generally with a high school education. Nothing against that, but the levels of training and motivation are variable. There is little or no quality control. You're sent out with your methane sensor, told to do the job, and you come back and say, I did the job. That's the quality control we have in the oil industry. Cost is the primary consideration, and therefore, speed is valued as much or more than accuracy. Let's get the job done, right? It's hot out here, it's cold out here. I've been in both situations, believe me, to the limit. And so all these things promote what I call checklist thinking. Finish the job, tick the marks on the sheet that you're given, do all these things, and call it a day. And again, I'm not running down the oil and gas industry in which I spent the better part of my life. But this is the reality.
It's never going to chime in. So in terms of the cost, so, I mean, is part of this a result of gas being, $3 and 1 BTU forever? Or like with, there's a lot more gas infrastructure now than there was when it was 8, 9, 10. But does it even come close to penciling out where like either the pipeline operators or the sources are saying, well, I'm going to lose a lot less of my product? And what does that look like on paper?
Right. Well, you will note that I do not have the chart widely published and reproduced, including from the International Energy Agency, which shows that kind of half of methane leakage will pay back if you repair it. If that were true, it would have been done.
Yeah.
Right? These people know their economics really, really well. You have to consider the cost of capital, the competition for capital within a company. So you're given a certain capex, are you going to spend it to replace valves, or are you going to drill a new well? Drilling a new well is more profitable. Yeah. So I think that this idea that repairing leaks, certainly in the upstream, before you get into the transcontinental pipeline, that's a different world actually, but certainly upstream, the wells, the gathering lines, the compressors, and so on, because it's so dispersed and the leaks are hard to find. I think that this idea that we get a payback is a fairy tale that the environmentalists in the industry tell each other, in my honest opinion. Yes?
Very briefly, do the detection methods vary for cold and hot climates?
No. No. There are exceptions for Alaska. We'll get to Quataway later. There are exceptions for Alaska, but no, the techniques are basically the same. I'm not sure there's any substantial difference. Technical stuff, but I don't think there's any great dispersion in techniques. Yeah.
Are the routine methods being used by the industry are comparable to those academic studies in terms of how did it detect it and all that?
We're going to talk about that in a couple of minutes.
The answer is no.
Correct. The answer is no. Yeah, let's just cut to the chase. Okay, so what methods are being used now to sort of monitor and try to quantify leaks in the industrial setting versus our top-down, bottom-up academic approach? So on the right, there are these sort of green and blue bars. This is data, by the way, from 2,500 oil and gas wells in Lloydminster, which is on the border between Alberta and Saskatchewan, Canada. So on the right are sort of these green and blue bars, which are basically, the green bars are reported methane venting and flaring, and you convert the flaring into a methane load from slip and so on. And the blue is basically sort of an emission factor approach. So let me explain. So when you vent gas, which sometimes happens in the course of ordinary operations, you can sort of maybe estimate how much you're venting, and that's what's reported to the Canadian government. The blue part is what's called the emission factor, which is basically a census of all your components. So each component, there's valves. Some of these valves are operated by natural gas and actually emit a puff of gas every time they're actuated. This is not a great design, but that's how it is. So you've got components, each of which are expected to emit a certain amount of natural gas in normal usage. So you count those numbers of components, you multiply by the emission factor, then you add up all the other components, and there you go, and you report that to the government. And lo and behold, you're doing better and better every year. Marvelous. But let's look at our top-down academic style measurement done with aircraft, where they're actually making a measurement. The difference, as you can see, and the vertical axis is in what? Tons per hour across this oil field. So this is the emission rate in tons per hour, going up from 0 to 30 tons per hour. And you can see that the top-down academic style measurement is like 3 to 4 times greater than what gets reported. Yikes. So you can replace valves till the cows come home, whatever, to make your emission factor look better. But there is this huge discrepancy between what's observed and what's reported. Now this is Saskatchewan. Maybe other places the discrepancy is not as large. I happen to find this, maybe this is just the worst case. But still, I think it's not completely unrepresentative. And the point is, I'm a physicist. And you're not going to give me a spreadsheet and tell me how much methane you're losing based on multiplying stuff. You're going to have to go out and make a measurement. And when I see this, I'm more convinced than ever that physicists and people with that mentality need to run the show. If we're going to understand what the problem is, how big the problem is, and then how to solve it. Okay. Right. So moving along to emission sources and detection methods. First of all, let's look at the sources. And there's been a lot of discussion about the spectrum of emission sources of methane. This happens to be kind of an interesting, sort of particularly clear study. It came out of some measurements that were done in the Barnett in central Texas near Fort Worth. Basically, the horizontal axis is basically a cumulative percentage of sites. So basically, the number of sites increases to the right with 100% of all the sites measured, which is 200 on the right. The vertical axis on the left is the cumulative percent of methane emissions from those 200 sites. So, and the sites are ordered in terms of emission intensity. The vertical axis on the right is methane emissions per site in kilograms per hour. It's on a log scale, but you see it goes like 0.05 kilograms per hour to 50 kilograms per hour at the top. And again, these sites are ordered according to how much methane they're emitting. And again, this was done with a Picaro truck-mounted measurement where they actually did the meteorology you need to get a leak rate from the basic measurements that you get from the Picaro methane sensor. So there are some interesting facets of this data, these data. One is that 38% of the sites contribute nothing, as far as Picaro can tell. So any time you spend hunting for leaks, as you saw in slide 2, here I am going around one joint at a time looking for leaks, that is a total waste of time for 37% of the sites. So right away, there's a 1/3 waste in effort. And which you can tell by driving around the fence line. These are fence line measurements. This is basically well sites that they could reach by driving on public roads, done without the permission of the operators. Looking at the rest of the chart, I've sort of drawn in some lines here. I drew a line at 95% of the sites. So 95% of the sites are to the left of that vertical line, 5% of the sites are to the right of that vertical line. If you sort of look at the curves, you'll see that 40% of emissions comes from 95% of the sites. 60% comes from 5%. 60% comes from 5%, which means that if you only go to 1/20th, the correct 1/20th of the sites, you knock your problem down by 60%. That leak rate at that 95th percentile site is about 5 kilograms an hour. So if you're hunting around for tiny leaks, you're looking in the wrong place, because most of the action is from the largest leaks. This is what's called the super emitter approach, and believe me, this is one of many, many examples where this has been done over and over again, and the numbers change obviously depending on where you go. Sometimes it's 80% and 5%, sometimes it's 50% and 5%. It's always heavily skewed, a heavy tail toward the large emitters. That's what they say, okay, for those statisticians in the audience. Let's look at another example.
Bob, can you just explain to those who aren't technical, what is the Picaro method? So they've got something on a truck, they're driving around and it measures?
Yeah. So it's a point measurement of methane gas, and sort of I think it's a chemical sensor. I should actually study up on that a bit more.
I can give it. You want?
Yeah, go ahead.
It's a laser box that we have it here too, and it's measure methane, can measure also gases, other gases in real time, in situ, and also the isotope ratios can tell you what's the source of the methane. You can confirm it's coming from the thermogenic rather than other potential sources. So you put it in a truck or airplane and do that in real time.
Thank you for this.
If it's a small number, they're doing the vast majority of the emitting, wouldn't it make for an easier testing procedure then? Shouldn't those be easier to see in a cursory drive-by?
Yes.
Okay, am I jumping ahead slides? Or?
No, that's exactly the point you're supposed to draw from this
Okay,
slide.
so drive faster by, and as soon as you catch one, that's probably a super emitter.
Well, yeah, I mean, once you get to the well site, it's not a big deal. I mean, these well sites, as you'll see later, are kind of far apart.
Yeah.
But yeah, you're looking for the biggest emitters, and those are the ones you have to focus on by going in and then finding what on that site is the problem.
With remote sensing, are we approaching any satellite methods that
We're getting there.
Okay.
Yeah.
All right.
So my question was going to be, is related. There is yet no way to predict which are these big emitters, short of driving a car out to the well site?
Not that I know of.
And so it's not correlated with, the field services company or anything else? I mean,
Well, it would be marvelous if Schlumberger did a much better job. No, honestly, I have not heard that, and whether one drilling contractor is better than another, or supplier of surface equipment, I guess I would be surprised. I mean, there's certain standardization of that kind of well site equipment, but a lot of it depends on the quality of the construction and the welding and the bolts being tightened properly, and we'll get into a few other issues in a minute. Yeah, in the back.
I guess one other potential correlate might be, if there are spills or, sort of, obviously some of these are like tablespoon level spills, right? But if they're minor spills or some other sort of indicator that the construction wasn't, didn't
We don't have all these expert in the room here on spills. I'm not sure it's correlated because, again, you're dealing with gases versus liquids. Liquids are, okay, so I was up in Alaska where somebody had spilled 5 gallons of oil on the permafrost, and there was a crew out there with shovels and buckets remediating it. Okay, again, that's an easy pollution thing to find and fix. This is hard. It's not obvious. It's not obvious that your weld was bad. Yeah.
Can you talk about the factors that lead to such a huge discrepancy between, in terms of leakiness?
Yeah, I'm going to go into that in a little more detail in a minute, but I'll give you a preview. One is intermittent sources. I'll get to that.
Okay.
But the biggest problem is if there's intermittency. So it could be that when they drove by a well that showed up really hugely bad, it could have been because something bad was happening in that hour. I mean, they were surveying 200, so it's using the ergodic theorem, you're replacing time with sampling and so on. But I suspect that a lot of the worst leaks are intermittent leaks, and we'll talk about that a little bit. Yeah. Brian, yeah.
So I actually did this for my undergrad senior thesis, driving around the Marcellus Shale region with the LiDAR sensor, and I had 20% of sites contributed 80% of emissions. And one of the ones that contributed the highest amount, actually, as we drove by, you could see the gas, you could see something was escaping, and that showed up in the photo, and so that could have been an intermittent example at that site.
It's always nice to get confirmation from the audience.
It's not your daughter, is it?
But to tell you the truth, I've had exactly the same experience. I climbed up to the top of a tank, somewhere in Texas, I guess, I forget where, and a hatch was open and coming out. Oh my God. I mean, right there. Yeah, same experience.
are we talking mostly extractive wells, correct? Or not, we're talking extractive wells that generally bring petroleum up from the ground, not wells that can inject.
Yeah, so there's injectors and producers, right, in the conventional secondary recovery scheme. And these are wells that are producing wells, yes, where gas is coming out, being collected, hopefully sent to markets, or flared.
I just want to make sure if I'm understanding my take-home message from this is, are you saying that there's nothing in the characteristics of the wells, certainly at the end of these distributions, that would allow you to be predictive about where you're more likely to find leaks?
The best predictive factor is whether the well was drilled for gas or drilled for oil.
And which is which?
Yes, so wells that are drilled for gas they tend to be much more careful about collecting gas.
That's a good. They've got pipelines to take it away, right?
And they have gathering pipelines to take it away before they put it on production. The problem with oil wells is that, especially with the tight oil plays, the so-called shale that's liberated by fracking, the problem there is that those oils are very gassy, which is basically their production mechanism. And the gas is, at best, a byproduct, at worst, a waste product. So people are none too careful about it. And so what you find is that although most of the gas in this country comes from gas wells per se, half of the methane on the estimates that we have come from oil wells, just because they're less careful. So that is, I think that's the only predictor that I know of, reliable predictor. Okay, let's move on to another example. By the way, that's good. Thank you. Okay, here's another. Again, there's lots and lots of this kind of data. This was an aerial survey of 392 abandoned wells, I believe, in British Columbia. Done aerial survey. So this was a shortwave infrared looking down measurement, and on the horizontal axis, again, it's sort of coded by leak size, with the abandoned wells with the smallest leaks on the left and the wells with the largest leaks on the right. In terms of 1,000 standard cubic feet per day, the M in oil field jargon is not million, it's 1,000. Very confusing for scientists. Vertical axis is the total volume coming out of each abandoned well in millions, millions. These are like Romans. Millions of standard cubic feet per year. And there's obviously a direct relationship between emissions per day and emissions per year, and that's represented by the lines. The lower line represents the one-to-one correlation between daily and annually emissions for one well. Second line is 2 wells. You got the picture. So basically the story here is that of these 392 abandoned wells, 367 of them contribute 20%, and which is 94%, and 6% contribute 80%. Oh my. So if you're messing around with 367 little wells, you are wasting your time. You are wasting your time and money. And regulatory burden is something industry takes seriously. So this is a great example. Okay, so now we're going to get into the detection modalities, and someone has already mentioned satellites, and that is a really important topic because over the last, kind of decade and a half, people have been launching Earth orbiting satellites, low Earth orbit satellites, typically like 500 kilometers above surface, to look for methane. And generally speaking, they're looking at it on sort of a global basis. They want to do a methane inventory of the whole world in typically like 500 or 1,000 kilometer swaths. So you've got this sequence of satellites that have been launched. GOSAT is the Japanese government methane monitoring. A lot of these monitor both methane and CO2. So it's a greenhouse gas satellite from Japan. They've launched the second one, and the launch date is shown in the second column. And the detection threshold for a point source is shown in the third column. And you can see that technology has been improving in kind of a nice way that we like. And GOSAT-2, which was just launched last year, can detect point sources at 4,000 kilograms an hour. Let's come back to this chart in a minute, but okay, tell me about 4,000 kilograms an hour. Well, let's look at Aliso Canyon, which undoubtedly was the largest single leak of natural gas in recent memory, near Simi Valley, California, for you Californians. Basically, it was leaking for 112 days, which is something like 2,700 hours. Total loss was something like 100,000 tons of methane, plus some ethane, which is a natural component of natural gas, which gives you an average leak rate of 36,000 kilograms an hour. So GOSAT was up at the time, and GOSAT detected it but didn't image it. These are not imagers. These are this will detect a world-class leak. Generally, they're used more or less just to get atmospheric concentrations. So that's kind of the way they work. Now, GHGSat is an interesting exception. GHGSat was launched by a Canadian company specifically to find and measure methane leaks on contract basis, because unlike these sort of global survey satellites which measure in wide swaths, so you sample the whole world every week or so, GHGSat has a very narrow field of view, 12 kilometers field of view, highly focused on where the customer tells it to look, and nothing around it. And when you have that tight focus on the infrared detector, then you can actually see leaks which are sort of more in the interesting range. And so when they launched it, it was something like 250 kilograms per hour detection threshold. Recent paper with better improvements and better meteorological model, which is what you need, 70. So, but still pretty far above the 5 to 10 that we were looking at in those so-called super emitters early. So satellites are really not quite there yet. Obviously, we're hopeful on the GHGSat approach that it will get better. It is certainly the only way you're ever going to find leaks in Russia. Yeah. Highly worthwhile to continue that effort, and the people at GHGSat are really good guys, and so we're Let's add aircraft to the list. Now this is getting more interesting. So I put the aircraft at the bottom of the table. There's two flavors. Aircraft with passive detection, shortwave infrared. And then the more advanced model is LiDAR, which is a laser method, which uses a laser to illuminate the methane. And it's much more sensitive. It's also in a somewhat narrower swath. But now we're starting to get into the interesting range of detection limits. And when you think about the million wells, and you think about the hundreds of thousands of miles of pipes and the hundreds of compressor stations and so on, airborne is looking better and better. So my dear former colleagues at Schlumberger did an economic assessment of the LiDAR active sensing method mounted on a Cessna 206. And using the parameters provided by Bell Aerospace, which deploys this method commercially. And they came up, and this is kind of an interesting study. So the airplane is launched from the airfield, which is that black dot kind of at the top. Airfield up there, this is the Permian Basin, this is Lubbock, Texas. At each colored line is a path that visits groups of wells around Lubbock. And then at each black dot, it stops, and you can see the inset on the lower right. At each dot, there's a series of well pads, which then are explored by sort of mowing the lawn back and forth, with the Cessna going back and forth and back and forth. And they figured out how long it took the plane to turn around. I mean, it was actually a very good study. And what they came up with was, at commercial rental rates for Bell Aerospace and so on, it turns out it only costs between $20 and $200 per well pad inspection, which is pretty cheap. I mean, that is very affordable, kind of an industry sort of thinking. So this looks, and again, the sensitivity is more than enough. Find the super emitters with aerial survey and go to the bad ones, and then do whatever detailed investigation you want, and go fix it. So this looks like a great way forward. Sounds good, doesn't it? Why am I here? Why is this a problem?
On drones, or does it have to be aircraft?
It turns out that aircraft is sort of more efficient.
Okay.
Drones can remain airborne for a half an hour, then kind of go back in the world. So you really want a fixed wing. I mean, helicopters are useful in some cases, but This is spread out over like large landscapes. West Texas, aircraft is the way to go. But people have put LiDAR on drones. So technically, yes. Okay, why am I here talking about this and why are you here sitting to this rant? Neither satellite nor aircraft method satisfy current leak detection and repair regulations. Environmental Protection Agency has rules for how to find methane leaks, and those rules do not permit satellite and aircraft. Now, they don't specifically say you can't do it, but these are not approved methods. Which brings us to current leak detection and repair regulations. Why are you smiling?
You know, I like regulation.
I know,
Talking about
lawyers love this part, yeah. And Kate, please, I might be running off the rails here. If so, just stop me. No, I'm not joking. I'm not joking, because this is fairly new terrain for me. Okay, so 2016 Obama era Environmental Protection Agency leak detection regulations are, in my humble opinion, ridiculously prescriptive. And I'm going to give you an example of that. So the methane detection regulations are encoded in 40 CFR 60 Quad OA. That's what the people in the field call it. OOOA, it's some part of this Code of Federal Regulations. And 2 methods are permitted. One is called Method 21. God knows what the other 20 methods were. Possibly even worse. But let's look at what is specified in terms of what you need to do to satisfy this rule. The scale of the instrument meter, this is a direct quote from the Code of Federal Regulations. The scale of the instrument meter shall be readable to plus minus 2.5%. The nominal sample flow rate, as measured at the sample pro tip, shall be 0.1 to 3 liters per minute. And the instrument shall be equipped with a probe or probe extension not to exceed 1/4 inch in outside diameter. Folks, I am a professional instrument maker. I have 39 US patents. I'm a member of the National Academy of Engineering. If my management gave me these specifications for a methane leak detector, I would refuse to work on the project. This is ludicrous. When my boss told me to build something, he said, Bob, this is what we want. Go figure out how to do it. I was not told what the probe diameter was. So I don't know why these rules are written this way. I'm in the process of interviewing a wide cast of characters and range of players who might be able to answer these questions. But to do method 21, as I was doing on slide 2, this is the equipment that you have to use. So the other part of the frustration is it's hard to understand how leak indications, as encoded in the Code of Federal Regulations, actually relate to methane emission rates, because none of the methods that have been approved actually measure leak rate. Leak rate is actually hard to measure, because to do it right, and the people who do this, the bottom-up people and the top-down people know this extremely well, you need to measure the concentration of methane in the plume, because you always have wind at these damn well sites in West Texas. I can tell you that from personal experience. You have a plume of methane, and you need meteorological data. You need wind speed, humidity, blah, blah, all that stuff, to put into really complicated models, which are pretty controversial among the people who specialize in that sort of stuff. But they're controversial in kind of a nice way, because let's work together to improve things, but they're complicated models. And then maybe you can work backwards from your data, which is concentration as a function of distance from site, work back to what is the source, what is the strength of the source. However, none of these methods that have been approved do that. So the method 21, which is the probe, the 1/4 inch probe that you have to use, basically regulations tell you you have to fix a component if the reading is 500 ppm. What does that mean? 500 ppm has nothing to do with liters per hour. Nothing to do. It depends on how far you are. I think you have to be like within an inch, but it makes a difference whether you're a half inch or 1 inch. I can tell you that from personal experience in a 5 mile per hour wind. Now, there's another alternate technique called optical gas imaging, which is more popular because it's a lot easier to use. And that's like an infrared camera that sort of looks at the scene, and maybe you've seen pictures of this in the press and so on. You see sort of various clouds and plumes that represent methane, natural gas leaks. But what the EPA tells us to do is we have to have optical gas imaging equipment. This is the last paragraph. That must be capable of imaging gas that is half methane, half propane at a concentration of 10,000 ppm at a certain flow and from a certain orifice. Let me tell you, oil field natural gas, I'm an expert on this subject. Oil field natural gas is roughly 900,000 ppm methane, with the rest ethane, propane, butane. So the requirement for this optical gas imaging has nothing to do with real oil field fluids. Nothing to do. Way too much propane. The concentration is, what does it mean? So these are nonsensical. And again, I'm in the process of, if anybody here is from Research Triangle Park, you can start throwing tomatoes now, but I want to interview you because I want to know where the heck this comes from. A lot of this came out of studies that were done in the 90s, I think for explosion monitoring. I mean, again, safety is paramount, and maybe in some circumstance you have this as an explosion hazard, but it has nothing to do with oil field practice. Nothing. Moving on. One thing that is in the 2016 regulations is an opportunity to propose to the Environmental Protection Agency alternative means of emission limitation, AML. And this is incredibly restrictive. So, for one, the only person that can apply for an alternative means certification are the regulated entities. This goes back to the Clean Air Act, which are the owners or operators of affected facilities. But they have very little interest in developing new technology because they're running gas fields. They're not building instruments. I'm the guy that wanted to make an application, but I couldn't because I'm not the owner or operator of any facility. So I don't have the right to go and ask in present regulation. Then the applicant must collect, verify, and submit test data covering a period of at least 12 months. That means for a whole year, you need to run the approved methods, method 21 or optical gas imaging, together with your new method at the site. Because this applies to each affected facility. That means every well site needs to get separate approval for the new method. Guess how many times there's been approval of an alternate means of emission limitation? Take a guess. 0. Yes, I heard it from a few places. 0. Never been done. Okay, let's look at the 2018 reconsideration of these rules, Trump era. Now, perhaps you read about this in your Energy and Environment News, Wall Street Journal, where it's been widely publicized. So Trump administration comes in, we want to relieve industry of these horrible, burdensome regulations. So what they do is they reduce the number of inspections, which is guaranteed to increase the amount of methane emission, no question. That's easy to model. You cut the inspections by half, you're going to basically kind of double the amount of methane that's going to go into the atmosphere because you're only detecting leaks half as often. Duh. They justified this on the basis of a social cost of methane, which we will talk about later if I have time, which is highly controversial. Okay, fine. But the way these regulations work, and again, the experts can chime in here, but according to the Administrative Procedures Act, it's very, very hard to change a regulation, really super hard. When we went to talk to the EPA people a couple of years ago, we said, hey, we're developing all these great new methods, but it doesn't really fit into your present regulatory scheme. And they said, well, it takes 4 years to change a rule. You have to go through the whole regulatory process all over again. And, honestly, it's not docketed until, like 2040. Well, of course, we took that back to our management, and they showed very little interest in supporting our work on developing better methane sensors, needless to say. So Trump comes in, and these rules are sort of like Pandora's box. You know, you open it up and bad things fly out, but it gives you the opportunity to get inside. So we don't have to wait till 2040 anymore. The rule is open now for modification. Yes, it's open now for modification. And you can modify anything you want, not just what Trump proposed. So, but what they did propose was an individual application can cover multiple sites, and applications can be made in conjunction with manufacturers or vendors. That's a good thing. And applications can be grouped with various sites and basin specific. So overall, it's friendlier, it's innovation, but still the focus is on component level leakage, which again ignores the whole super emitter thing. So yeah, Trump seems to be a friend of innovation, who knew? But they didn't go far enough. So I and many other people pointed this out in the public comment session, which garnered 100,000 comments, most of which were nonsense, of course, but a number attacked this particular paragraph in the code. Still, we need to go further. So, for example, gathering pipelines. This data was discovered accidentally as Aerospace was flying from one well site to another. They saw this huge plume. There was no well down there, but it's where gas pipeline had been buried and broke. Gigantically, unregulated. Here's a charming example, the unlit flare. Flares are used in normal, you look pained.
Yeah, sorry.
Flares exist to burn off gas. It's a safety factor in normal oil field operation. Fine. Sometimes they just don't get lit. They forget. Yes.
Just to clarify, is this unregulated or is this an unenforced regulation?
You know, honestly, I don't know. I mean, I assume people want you to light your flares. I don't know if you can be fined for not doing it. It's certainly accidental. I mean, no one would do this on purpose. But it happens. And I was at the AGU last fall, American Geophysical Union, and there were several examples of this in various papers.
I mean, I guess my sense is that as an operator, there's no particular cost to
absolutely not.
To not lighting your flare.
Absolutely not.
Outside of whatever enforcement penalty you might face.
Exactly. No, it's nonsense. But the problem is that, like we were talking about intermittent sources, this is an intermittent source. Now, a day later, they'll remember, oh my gosh, we should have lit the flare. And then they report their emission factor, 1 lit flare. Got it? So, yeah, to call it unregulated might be a bit fair, but it's certainly unmeasured, undetected. So, I'm going to wind up in the next 3 minutes. Objectives and methods of rational regulation. Where do we go from here? Objective. Present practice is to eliminate all emissions, with a few exceptions, from new wells and compressors, no matter how small. And you need to do that. If you find it, you need to replace the valve, no matter how small. An improvement would be a phased reduction of national total methane emissions. Let's look at this on a national scale, which is exactly what I proposed in my comments to the EPA. You need to look at this on national scale, which means you need to go after the super emitters and not worry about the minimal stuff. In components versus site, the present practice is a component level inspection, which promotes a checklist thinking where you're going to check every valve, but you don't worry about the unlit flare, because it's not in your checklist. And it's laborious. It's most likely to miss the most important emission sources, which are intermittent. Potential improvement would be site screened by mobile platforms, hopefully fairly frequently. Present practice is, right now, all new wells and compressors are examined and there's a reduced emission completion guidance and so on. But what we really need is comprehensive emission of major greenhouse gas emitters from all parts of the national gas supply chain, including the gathering pipelines that are buried and unmonitored. And the LNG, liquefaction terminals, which are unregulated and unmonitored. I talked to Meg Gentle about this yesterday. We need not to examine every component, but only the biggest, the most problematic ones, the super emitters. I've talked about that. We need to worry about continuous versus intermittent sources. If you have a semi-annual inspection, Obama, or annual inspection, Trump, you're going to miss the intermittent sources, which are often the largest sources. And that's the stuck tank valves. This is what, I guess you're still back there? Yes. Stuck tank valve, that's what we observed. The open thief hatch, the unlit flare. The potential for future improvement is time and spatial continuous surveillance. So that even goes beyond aircraft, unfortunately. You might have to put a sensor at the site to stare down at your site to see if something bad is happening, even intermittent. And we don't yet have, certainly nothing commercial that is in that space. So, yeah.
Wait, really? Like there's no SCADA type system to monitor if your flare is working all the time? It seems so simple.
You would think there would be on the flare issue, but certainly not on the tank issue.
On whether your tank hatches closed?
It would be easy to, it would be absolutely dead easy to do.
Sorry for being so incredulous.
It would be absolutely dead easy to
monitoring
do.
pipelines in this way for decades.
Sure. I myself, two of us in the room, have personally seen this happen. So, no, those systems must exist. It's dead easy. I could sit down right here in 10 minutes and draw you a schematic. But it's not implemented on a large scale. Yeah.
This might exceed the scope of your talk, but how do EPA regulations compare with, say, EU or Saudi regulations or Russian regulations?
Yeah, that's interesting. I talked to someone from the European Commission yesterday. I was in Brussels a year and a half ago, meeting the same woman, and I said, hey, we're worried about this methane emission problem, and I got blank stare, like, methane emissions? Never heard of it? But I guess we'll let the Americans take care of it.
Okay.
So that's exactly what they said. I talked to her again yesterday, a year and a half later, and she said, yeah, this is a big program. We're about to submit a major report. We started thinking about it about a year and a half ago. Okay, I'm not claiming credit for anything. It's just an interesting coincidence, okay, whatever. And it has been more in the press lately, so I think it's been in the air. So they're just really getting started. I'm not sure anybody is, I don't think the Canadians are doing it any better.
Canada just implemented national regulations on this in the last year and very much tracked what the US had done, and actually went through this same process with about technology for leak detection, where their proposed rule was very prescriptive. And then some of the vendors like General Electric went in there with Baker Hughes and said, look, we've actually come up with these cool new sensors and we can't figure out how to deploy them in the field because you're not making it easy. And so they made the very same change that the Trump administration is suggesting here, to allow a little bit more leeway in the type of alternative technology that you can bring to the regulator. Explicitly, we're looking at Colorado state methane regs and 2016 EPA regs when they wrote the Canadian ones.
Yeah, and just to expand on that point, I think the states are really where to go. I mean, the states are much more proactive in Colorado. It was a good example. California.
New Mexico may be getting
New Mexico,
really
yes,
interesting too.
absolutely.
Right.
Washington's sort of bollocks. And honestly, for those who are interested, I would be working at the state. Well, I see it's just past 11. I'm not going to show you the last slide on social cost of methane.
We have to 11:15, but...
We have to 11:15.
Yes.
But I can show the last slide on social cost of methane.
People can...
If you don't mind. Or you can move. But one way that we grade our regulations is what's called the regulatory impact analysis that goes along with every regulation. And in the field of greenhouse gases, the standard method is to look at the social cost of the emitted gas, either carbon dioxide or in this case methane. Now the problem with these social costs is that they are highly dependent on the input assumptions, particularly the discount rate. This may seem obscure to those of you who are not professional economists, but a low discount rate basically says, we've got to worry about this problem way into the future. The next generation is going to be impacted by this problem. That's a low discount rate. High discount rate is, the problem's going to go away in a year, and okay, it might be a big problem for a year or two, and then we don't have to worry. Well, guess which way? That assumption has been changed over the last 2 years. So here's my schematic regulatory impact analysis. On the horizontal axis is fraction of methane emissions abated from 0% to 100%. We want to abate everything. That's on the right. The vertical axis is the cost or benefits denominated in dollars. And 0 is not at the bottom. 0 is actually displaced upwards because, in fact, let's assume that abating some methane emissions does give you a payback, as those charts show, as Brian mentioned earlier. I'm not going to say it's a lot, but yeah, there is some payback on not letting the methane get away, but putting it into your natural gas system. But the green lines represent the social cost of methane. So if you have a high social cost, in other words, if methane does a lot of damage over a long period of time, Professor Schindel of this institution, in the audience? No.
He sends his regrets. He's at Appalachian State today, but
okay,
yes.
Fine. Anyway, he estimated $2,400 to $3,600 per metric ton of the social cost of methane based on a 1 or 3% discount rate, in other words, the long-term damage. It also included an international component of damage because this is a global problem. Trump administration Executive Order 13783, remember that number, mandated that costs, that benefits be discounted at a 7% rate, which is a short-term financial return type rate. Got it? And only within the boundaries of the United States, which basically, depending on how you carve it, geographically, population could be as low as 6%. So you can see that the amount of abatement, which is the red line, very much depends, and this is just a schematic, on what your social cost assumption is. Honestly, we need to do better. This is an unsolved problem of economics, that this kind of impact analysis depends so critically on the fine details of the assumptions. This is an unstable system in both a regulatory sense. I mean, from a physics standpoint, this looks unstable. And this is an open question about how to do this better. So I'm just going to end with a small advertisement. I'm working on a legal and economic study of 40 CFR 60 Quad OA. From a technologist point of view, this has been done a lot by lawyers, by economists, by policymakers. My special lens is the guy actually building the instruments. My question is this regulation likely to succeed in its goal of reducing vented and fugitive methane in a cost-effective manner, whatever regulation you might write? Does this regulation encourage or discourage innovative approaches to addressing the conditions it seeks to remedy? Certainly the present rule discourages innovation. I saw that for myself. Successive administrations have calculated the cost-benefit ratio of methane emissions in very different ways. For the sake of regulatory stability, can broadly shared principles of cost-benefit analysis be formulated? That's something that's outside of my domain of expertise. And as a sort of side note, can the deregulatory agenda of the present administration be retasked to explore ways of reducing regulatory burden while retaining essential purposes of regulation. Opening up those rules. Every time you open up a rule, it gives me the chance to go in and tinker with everything inside of it. We should be taking advantage of those opportunities. Thank you for your attention. This is Heather Conklin.